In Chapter 11, we'll learn about the USB port and its features. We'll use a TivaWare example in the lab to experiment with the operation of the port. The USB port on the TM4C1294NCPDT is USB 2.0 compliant at 12 megabits per second full speed operation. It can also operate in low speed mode at 1.5 megabits per second. USB 2.0 high-speed operation at 480 MHz is possible with an external PHY using the ultra-low pin count interface. Power management support is available to reduce power consumption during intermittent use. The device has an integrated PHY or physical interface so that the hardware connection to the USB port is very simple. All the normal transfer types are supported: control, interrupt, bulk, and isochronous. The port also supports DFU, or Device Firmware Update, in ROM, for both host and device operation. This means the device can be plugged into a host and the DFU can accept update files. It also means that the device can act as a host and download update files from a properly formatted device like a flash drive. TI is a member of the USB Implementers Forum, and Tiva is approved for use of the USB logo. The stacks, the hardware, and so on are certified USB compliant. We also offer vendor and product ID vid-pid sharing so that you don't have to purchase the codes. You simply sub-license ours. One of the biggest additions to the TM4C129X family is the support for high-speed USB with an external ULPI PHY. It can now support low speed, full speed, and high speed with the external PHY. ULPI reduction in pin count is achieved by allowing the relatively static UTMI plus signals to be accessed through registers and by providing a bidirectional data bus both for the USB data and for accessing register data on the ULPI transceiver. It also fully supports the USB on-the-go supplement, allowing VBus to only be powered up when required and to be turned off when the bus is not in use. The block diagram for the USB peripheral shows the integrated USB controller and PHY that offers up to 16 endpoints. Enumeration requires a dedicated control input and a dedicated control output endpoint. There are up to 7 additional configurable input endpoints and 7 additional configurable output endpoints. The controller module has 4K of dedicated endpoint memory, which is not part of the device's SRAM. DMA is supported on 3 separate in endpoints and 3 separate out endpoints. For bursty data, one endpoint can utilize a 1023 byte double buffered buffer from the 4K memory. Like the Ethernet module, the USB module is a DMA master. It can transfer up to 8 transmit and 8 receive endpoint channels. TivaWare's USB library supports host device and on-the-go operation. It's built on the Peripheral driver library's API set. This construction adds a framework for a generic host and a generic device functionality that you can build on. It includes implementations of common USB classes. The construction of the framework is layered so that the designer can decide on the amount of abstraction they want to utilize. Drivers and INF files have been included where needed. The list on the right shows some of the device examples and supported Windows features included in the USB library. There is also a number of host examples, but since the kit does not include the adapter cable, we'll leave those for you to investigate on your own. The USB library's APIs are built on top of the Peripheral driver library's APIs. You can decide what level of customization that you want to deal with. Take a look at the far left, Application 1. Here you want to pass simple data to a higher level API. This would be a customization of an existing device, in this case, a custom human interface device like a mouse. As you move to the far right of the chart, your level of customization increases to the point where you might be implementing your own USB protocol, or write or purchase your own USB stack. Obviously, on the far left of the chart, less time will be spent developing the USB software, while on the far right, the developer has much more control. Where should you start? For an application that involves implementing its own USB protocol using DriverLib, working with USB driver API will be a recommended approach. This provides the lowest level of abstraction, giving the user the most amount of visibility and control. This is represented in application 4 in the diagram on the slide. For applications in between, like examples 2 and 3, a user can pick and choose a level of abstraction that's not too low or too high. Note that devices that resemble existing applications, and many do, require significantly less new code. In Lab 11, you'll use a TivaWare code example to implement bulk transfers of data from your laptop host to and from the USB port on the LaunchPad. You'll use a small Windows side application to send and view data while also watching messages on the terminal display. You'll also use the emulator to view the transferred data in the microcontroller's memory.